Going to be looking at lesson 2, factorial notation and permutation. So I'll probably split this out into 2 videos where I do section 1, just kind of the notation itself, and then I'll do section 2 with all the word problems. So when we are talking about factorial notation, what we are talking about is this idea that, okay, as soon as we start seeing successively smaller things being multiplied, that is such a frequent occurrence in mathematics that we actually have a special notation for it. So n factorial, or any number factorial, basically means we're going to take that number and multiply by one fewer than it all the way down to 1. So for instance, 10 factorial is 10 times 9 times 8 times 7, blah, 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 all the way to 1, okay? And in our class, and at this level of mathematics, things other than a whole number positive, or I should say just positive integers, don't mean anything mathematically. So 3.2 factorial, negative 5 factorial, pi factorial, you can just say they have no value, okay? There are some other domains of mathematics that do, assign some values to them. But for us in this class, you're always going to just get, positive integers and evaluate them. And we do have a special case of 0, because I did say positive integers, which would imply that 0 would not be included in that. But 0 factorial actually does have a value assigned to it and is very important to us, and it evaluates to 1, okay? So there are kind of, it's like one of those things where you can just, ignore me, skip ahead a minute, and move on. But if you're looking sort of for an explanation for it, I kind of have 2 different ways of explaining for it. So the first one kind of harkens back to the idea of whenever we're using a factorial, it's like we're figuring how many different ways to arrange a set. So for instance, if I have, 4 people seated at a table and I'm wondering how many different ways I can arrange them, or 4 people, lining up to take a picture, how many ways can I arrange them? Well, it's 4 factorial because it's going to be 4 times 3 times 2 times 1, and that gives us 24. So let's say I have 0 people and I'm wondering how many ways I can arrange 0 people. Well, 0 factorial then, if I'm applying that logic, you might want to say, okay, there's 0 ways to arrange 0 people, but that's actually incorrect. You have one way to arrange 0 people, and that's to have no people at all. So that is the way to arrange 0 people. It's it is 1. There's exactly one way to have an arrangement of 0 things. The second, maybe more mathy way of looking at it is to sort of establish a pattern here, where we can say 3 factorial is equal to 4 factorial over 4, which kind of cuts ahead to what we're going to be doing here in a second, but just to show you what's going on here. So 4 factorial is 4 times 3 times 2 times 1 all over 4. So these can cancel, which gives us 3 times 2 times 1, or 3 factorial. So that's sound. So if we apply that logic all the way down, I'll go here just to kind of skip a few steps. So I'm going to have 2 times 1 over 2. Well, these cancel, and I'm left with 1. So then if I go here and I say, okay, 1 factorial is literally just 1 over 1. 1 divided by 1 is 1. And again, so I've got this other situation here that leads us to this logical conclusion that in order for our math to work here, and especially once we get into the actual notation of permutations, in order for us to use the permutation formula correctly, we've got to have the situation where 0 factorial evaluates to 1 rather than 0. So just a couple of algebra things here in terms of just manipulating and working with simplifying factorial expressions. So for instance, if you have a factorial over a factorial, that evaluates to 1. And this holds true for any factorial. So let's say I have any factorial over any factorial. So let's say I have a minus 7 factorial, not there, over a minus 7 factorial. That also evaluates to 1, okay? Which is going to become important to us as we do later questions. So let's look at 100 factorial times 98 factorial. Well, 100 factorial is going to be 100 times 99 times 98. And at this point, once I match up with the smaller of my factorials, I want to stop so that I can cross out these 2 things here. And this is basically the pattern that we're always going to follow with these questions, is you identify what is the larger factorial and you start expanding it down until you see the smaller factorial, okay? Because once I matched these 2 up, basically if I keep expanding, every single step I take is going to be canceled out. So why bother writing all those steps? I'm just going to write it as 98 factorial, knowing that if I were to expand times 97 times 96, blah, 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 same thing here, 97 times 96, blah, 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 that each single increment would cancel out. So again, that's what I'm going to keep doing. So let's look at this example right here, the third one. So hopefully you can see that the 5 is actually the larger one here. So I'm going to leave 4 factorial alone, and start expanding the 5 down. So 5 times 4. Hey, these match up now. So I'm going to write the 4 factorial because it still represents all the subsequent integers, and they match up. So they're going to cancel, keeping in mind that I'm saying cancel kind of flippantly there, but 4 factorial divided by 4 factorial evaluates to 1. So I still have that 1 in my numerator, and 1 over 5 is that answer. Okay, let's look at some more examples here. 12 factorial over 9 factorial. So 12 factorial clearly is my largest factorial there, so I'm going to start expanding down. So 12 times 11 times 10 times 9. Hey, I can stop because I see I've matched up with my second largest factorial, so I'm going to write it as 9 factorial over 9 factorial, 3 factorial. And these cancel, so I'm left with 12 times 11 times 10 over, I'm going to think to myself, what is 3 factorial? I'll just do this in a different color here. 3 factorial is 3 times 2 times 1, which is the same thing as 6. So I've got 12 times 11 times 10 all over 6. Now, with multiplication and division, it doesn't matter what order you do them in, as long as they all get done. So I'm going to actually, I see here that 12 and 6 are a nice divisive pair there, so I can just say 12 divided by 6 is going to evaluate to 2. So this is going to be the same thing as 2 times 11 times 10, or what's it going to be, 20 times 11, or 22 times 10, 220. Easier way to do that. Okay, same thing here. So clearly my 5 is the largest one, so I'm going to start expanding that. So 5 times 4 times 3, match that up. So I've got the 3 factorial all over, and then 3 factorial, 3 factorial. One of my 3 factorials cancels, and I'm going to be left with 20 over 6. And there's no common factors between 20 and 6, mainly because I know that, actually there is. I can look at that, I'm saying bold things. I can cancel it at 2. So I can divide, I can have this thing, and I can get 10/3 as a final answer. Okay, important to follow our order of operations. So anything going on inside the brackets, we evaluate first. So 5 factorial over 4 minus 2 factorial is 2 factorial. And again, I'm just going to expand the 5 out until I hit the 2. So 5 times 4 times 3 times 2 factorial, 2 factorial, cancel, cancel, is equal to 20 times 3 is equal to 60. Okay, so let's, up till now, all these examples have had numbers, aside from our first one where we were just talking about the idea. So let's look at stuff with actual variables in here. So again, I still follow that same principle through, where I'm going to expand the larger one. And in this case, my larger one is n plus 1. Well, how do I know that? Well, if I have some number and I add 1 to it, and then I have the same number and take 1 away from it, then clearly if I've added 1, then my numerator is going to be the larger in this case. That's not always going to be the case, but here it is. So I'm going to start expanding the n plus 1. So n plus 1, and then I'm going to do 1 less than n plus 1. So if I take 1 away from this expression here, that just leaves me with n. I still haven't matched up with this, so I'm going to expand again. So I take 1 away from n, and what does that look like? Hey, that just looks like n minus 1. And now I've actually matched up with my denominator, so I can write that factorial sign, rewrite this as n minus 1 factorial, and now these cancel. And depending on, the teacher and the question, you might want to put that together. So this is easy in this case, so I'm just going to put it together, but just know that, depending on the situation, sometimes it's fine to leave it in this expanded form. So let's look here. I'm going to figure out what is the largest one. And again, I see that n plus 3 is clearly larger than n plus 1. So I'm going to start expanding the n plus 3. So I start with n here. This n is this one here. So I'm just going to carry it down. And I start with n plus 3 times n plus 2 times n plus 1. Lo and behold, they match up now. So that's a factorial. N plus 1 factorial. Cancel, cancel. And I'm left with this cubic function here, so I'll distribute the n, so n squared plus 3n times n plus 2, and I'll distribute that in, so that'll be n cubed plus 2n squared plus 3n squared plus 6n, and that's going to equal to n cubed plus 5n squared plus 6n. And just a few more here. So, oh yes, the one with the negatives I want to do. So again, this can be a little bit trickier when I'm expanding down and I have 2 negatives. So again, this n minus 1 is the larger of the one because it has fewer negatives taken away from it. So minus 1 is larger than negative 2 is what I mean by that. So I expand this. So it's going to be, that's out of order there. So that's going to be n minus 1, expand it down to n minus 2, and they match up now. So n minus 2 factorial, n minus 2 factorial, cancel, cancel. Same thing here. In this case, though, my n minus 5 is the larger of the numbers, so I have to be careful there. So I'm going to leave my numerator alone, and I'm going to expand the denominator. So it's going to be n minus 5 over n minus 6, and then the n minus 7 factorial. These cancel, and I still have that 1 in my numerator, and then n minus 5, n minus 6, or 1 over n squared minus 11n plus 30. If we get into the situation of equations, it's going to be the same thing where I expand and cancel, and then I'm going to solve, and I'll have a linear or a quadratic. If I have a higher degree, I'm going to have to use some technology to solve, but just to go through the process here. So the n factorial is the larger one, so I expand that one out. So I'm going to get n times n minus 1 times n minus 2 factorial, because now these match up, n minus 2 factorial equals to 90. So I can cancel these. I'm going to move the 90 to the other side right now. So I'm going to have n squared minus n, and then I'm going to subtract 90 to get the 90 to this side. Because I've got a quadratic, right? Like if I just had a linear function here, just a 1n kicking around, I would just move all the numbers to one side and then isolate from my variable. Here, because I've got that quadratic, I'm going to factor it into two linear functions so I can solve them just like normal. So I'm going to have, what is that going to be? N minus 10 and n plus 9 is equal to 0 here. So then I have the answer. I'm going to change color so it pops a little bit. So n is equal to 10 or n is equal to negative 9. And then I've got to think to myself, okay, which one is it? And hopefully you guys can see that n has to be 10 in this case, because the only way for factorials to work in our little world here is that we have to use positive integers or 0. So we're going to say that n is equal to 10, with n being equal to negative 9 being non-existent, not valid as an option here. And same thing with this question here. So I'm going to expand this n plus 4 down. So it's going to become n plus 4 onto n plus 3 onto n plus 2 factorial, n plus 2 factorial. These cancel. Everything still equals 6 over here. I'm going to multiply in here. So this is going to be n squared plus, what is that going to be? 7. Wow. 7n plus 12 is equal to 6. I'm going to minus the 6 from both sides. I'm going to minus 6 from both sides, so I can set it equal to 0. So n squared plus 7n plus 6 is equal to 0. Or n is equal, or I'll say n plus, what's that going to be? 6 and 1, 6. And then n plus 1 is equal to 0, which gives me two options, n equals negative 6 or n equals negative 1. And now some of you might be saying, hey, doesn't that mean that both of them are invalid? Is there no way to make this true? But remember, it's not really about, now in this case on the left-hand side, because I actually just had a plain n equals, like it was just the n factorial, I knew right away that any negative wouldn't be valid. Here though, I've got a number and I'm adding 4 to it. I've got a number and I'm adding 2 to it. So in reality, I can have negatives because I'm going to immediately add 2 to them, but I want to test it out, because if I try putting 6 into the numerator or denominator, I end up with a negative expression inside my factorial. Whereas if I just add the negative 1, like if I just, kind of go up here, I say negative 1 plus 4 factorial over negative 1 plus 2 factorial. That evaluates to 3 factorial over 1 factorial, or 3 factorial. And we know that 3 factorial is equal to 6. So that holds true. Anyways, that's going to be it for this video. In the next one, I will do the word problems with permutations.